Before I begin my video, I just want to let you guys know that I have a patron, Vladimir Ivanov. If you guys want to support me on Patreon, just go to patreon.com/parsetreemaster. Thanks, guys. Welcome to part 2 of the Ackermann function. If you haven't seen part 1 yet, I highly recommend watching that one. Part 2 is basically just another version where we do memoization and we don't use recursion. So part 1 uses recursion and sort of introduces you to the function and what it is. And this part just gets a little more in-depth and a little more complicated to make a more efficient program. Thanks, guys. So what we're going to do is we're going to do Ackermann. That's what we're going to do. And the way it's going to work is we're going to start off in fact, and it's not going to be, and here's another thing. So there's two things that we're doing here. Number one, we're going to be remembering things so that we don't have to call it so much, and it doesn't take exponential time to solve. But number two, we also are going to be trying to make it so we don't have to call recursively. So I'm actually going to, from the beginning, I'm going to ask for m and n. Prompt m and prompt n. Okay. So now I'm going to get a matrix. Okay, I think I do 0 store into, and then I do a matrix A, and then I'm gonna call it 1 1. Okay, because I think the way the TI calculator stores the coordinates is it starts with ones for some reason. So I'm gonna have to add looking at the chart. Let's look at the chart really quick. Actually, that's going to be 1. Okay. Now, this is where it's going to get crazy. I'm going to have a loop. I don't know how I'm going to end the loop yet, but I'm going to say if m, yep, we're just going to do everything we did before. If m equals 0, then else, and then we're going to put an end. But inside the else, we're going to do another one. If n equals 0, okay, and we're going to do then, do else, and we're going to do end. Okay, so if m is 0, then we want matrix A right? We want n minus 1. No, n plus 1 to be stored into our mn. Okay, but remember, we have to add 1 because of the weird way that they set them up. Okay, and then in the other case, remember, so this is, so matrix A of m minus 1. Okay, but we otherwise would have put plus 1, so we'll just leave it regular m, comma 1. But remember, the base would be usually be 0. So in this case it would be 2. Is going to be our new matrix A, m plus 1, n plus 1. Okay, so notice how we're always depending on something smaller, which is good. That means that we would have to fill out matrix from the bottom up. Okay, else, now here's where it's like backwards, right? Because here's the problem. We have to build up the matrix to get there. So I just realized we can't depend on something smaller, because if we start with something big, we can never build up to it. Right? So an M, so when it comes to the building up the table, we have to be able to build it the right way, I guess. So maybe we just start with m and n being 0. And then we can just kind of make it print numbers however we want. Yeah. I think that's how we're going to have to do it. Right? Oh, okay. Well, no, that's fine. We can prompt, but what we have to do then is we have to then do another loop. So we have to do for, I think we have to do 2 for loops. Right? So we have to store m and n to like something like maybe x and y, just so that we can call them m and n still inside both the code and in the prompting, but like we'll call them master m and n, the x and the y. So and we can keep going until, so we can say while m is less than x, we can say and n is less than or equal to y. Right? And then we gotta do 2 n's at the end. Okay. Yeah, there we go. So we have to do, for m is 0 to x, and for n 0 to y. And we might have to switch those. I'm not sure yet because I haven't thought about which way the table goes. Yeah.
Okay, that's better. That means we won't necessarily... We'll see. Because I have to be able to... I have to make sure that I can always access whatever that memory is. Okay, so... Now here's an interesting one. Now I have to use... See, notice how I'm not calling a recursive function. I'm just calling a memory location. So it's not recursive anymore. Okay, so n minus 1, right? And that's going to be our continuation. Now remember, we got to add. So this is the inner call for that last part. Remember. Okay, so it's calling that inner a of m n minus 1, but then I added 1 to each one. So now I have m plus 1 and n to be that c. Okay. Then I have matrix A of m minus 1 and c. Right? But we got to add 1 to each of those because of the way they store it. And set that into our matrix A of mn, but add 1 to both. Okay. And now that should work. I don't know why I have this. Why I have the while loop actually, because if I'm doing a for loop to the x and the y, I don't need it. What? Yeah, I don't know why I'm doing that. I think I just didn't realize what I was doing for a second there. Okay, so Ackermann. So let's just test it on some numbers just to make sure it works. So if I put 0, 0, okay. Okay. I don't understand why we can't. Okay, 1 stores matrix A 1 1 0 0 1 What? I don't understand. Okay, let's try 0 0. Okay, we need to print it. So after this is done, we need to display matrix A of x, I guess x plus 1, y plus 1. Okay. Okay. So now if I do it again, and I do 0 1, oops. So what's m plus 1 and n plus 1 right now? Okay, so it's trying to store it in 1, 2, right? Oh, I think I know what I have to do. I think this is why. You have to set the dimensions, I think. So you have to actually... I think you have to do this. You have to do M and store dimensions matrix A. Or something like that. Let's try that. There we go. Okay, 1, 0. M2. Matrix A. What? Oh. Huh. You know, I just realized is N isn't necessarily set. Is it? Okay, so might have to switch these two. You have to figure, okay, so you have to go so here's the weird thing. So if you look on here, this is M minus 1, 1, not 0. This is a 1, which means if I haven't computed this one with the 0 yet, I can't even figure this one out. So what that means, I think, is that as long as I'm counting up the ends, it should be okay. Right. So I should be okay. So what I'm going to do is I'm going to say for n 0 y and try that. Okay, so if I put 0, 0, it should give me 1. If I put 1, 0, doesn't work. Okay, 0, 1, it works. That's not good. Okay, so what is this? What is this? If n is 0, okay, so on the table, how does this work? Right? On the table, how does this work? If m is 0, if n is 0 and m is greater than 0, if n is 0 and m is greater than 0, okay, if n is 0, which means the left column, and n is greater than 0, so basically everything on this left column, boom, 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 this whole column depends on the m minus 1, 1. Okay, so basically what it's saying is that this entire column is the same as this one. This is the same as this. This is the same as this. Right? This is the same as this. This is the same as this. So that means if I'm figuring out an m, I just iterate through all the n's first. If I figure out an m, figure out all the n's. Right? Okay. The problem with that okay, so you know what? That's probably okay here. You know what? I just realized this will probably only mess up with 1 zeros. It's probably only a special case with that. Because if you think about it, this column is the only time where it's a special case like that. I think you have to figure out... Do you have to... Does that apply to anything to the right of it? Because that's the only time where you're depending on something bigger, where it's like technically it's a 1. If you think about it, like we can figure out the like 3, 1 for example. 3, 1 should be 13. Okay, that didn't work. 2, 1. Oops. What is C? C is 2. Okay, if it's 1, 1, right, then you'd want 2 and 2 being the dimensions, which is fine, except that no, you wouldn't, because you'd want m and m minus 1. Okay. So maybe I did have this right before. So I do want 4 m is 0 to x on the outside. Now if I do Ackermann again, I should be able to get m and C plus 1. Hold on. Why is C 2? M plus 1 and N store as C. That doesn't sound very correct. No, that should be right, because M and N okay, what are the dimensions of the matrix then? C M and N. Is it that C is too big? M and C plus 1. Matrix A of M and C plus 1. M and C plus 1 store into M plus 1 and N plus 1. One, 3. That's weird. How did C get to be big? Do I need to add one to it? I mean, whoops. Right? 2, 1, 2. That doesn't sound right at all. It should be 5. Okay, so this is what I don't get. If this is working correctly, right, I should be able to have a C M plus 1 and N. My goodness. 4. I can't tell which one's the columns, which one's the rows. Okay, guys, I'm gonna have to pause it really quick. Part of the reason is because I have to actually go to the bathroom, but I'm gonna have to look at this for a second. I don't want to waste your guys' time, so I'm gonna try to figure out what the problem is. Okay, you guys, I am back here, and I've been messing around a little bit, and I noticed something kind of crazy. Now, maybe it's easier to show you with the table. So I haven't been paying attention, but you're not always just depending on another row on the side. You're actually depending on a growing number of rows to the side, and I'll show you why. So here you see I have a plus 5 here because first I added 1, then I added 5 because I was trying to get this to work. But actually, this is what I'm talking about. So right here, sorry. So you'll see that when I'm looking at this function by itself right here, this is strictly smaller because I'm just reducing n, so I'm just going like left in the table. When I reduce m, I'm just going up in the table. But when I have m minus 1 and then I have this, whatever this happens to return, now the table depends on where I'm going. The table depends on what is in the table. You get what I'm saying? So if this number here is huge, which by the way it does jump up, so it's not going to be 4, 5, 6. This is going to be a bigger number, and I mean a bigger number. But already this 5 right here, it's saying how far to the right I'm going to be going when I'm trying to calculate what this next one is. It's going to be going far to the right, not just one more to the right, but 5 to the right. It's a growing thing. So what I've been messing around with here is basically trying to figure out how I'm going to deal with that, and I've came to the conclusion that I might as well just, instead of trying to increase all these n's that I'm calculating beforehand, because that's not going to work, because then the table is going to be square. It can't be square. That's basically, or it can't be like rectangular. It has to be whatever shape allows it to just fulfill all its dependencies and still be finite and still be a table. So just by definition it can't be a rectangle then, because then you'll have ends that depend on ends that are further to the right. So what I'm going to do is I'm just going to set the dimensions normally, just leave it alone, and then I'll expand it dynamically. So what I'm going to do down here is there's one place that is really going to need to grow, and that's this. Okay. So this isn't going to necessarily be big enough. And if it isn't, then I sort of like need to start over, or yeah, okay, yeah, that doesn't make any sense. Trying to think how to do this. I could make the table the matrix bigger, but now I have the problem of I expanded it pretty much bigger than what I needed, and therefore I would need to use recursion to figure out how far to the right I'm going, because I can't just add to the loops here, right? I can't just like say like, oh, by the way, go back in time and finish more n. Oh my goodness. So guys, I kind of want to give up on one of my two goals, which was to make it so that we didn't use recursion. I kind of want to use some recursion. Oh man, I think I'm gonna have to finish this tomorrow. Can we do this without recursion? I'm not sure. This is crazy. Oh my goodness. So we have to figure out you might as well just use a recursive function. Like you might as well the whole if statement, which tries to calculate something for a number, it's almost like I can't predict what numbers I need. It depends on the function itself. So it's chaotic in a sense. It reminds me of the Klotz conjecture. I don't know, guys. I don't even know if I should bother trying to do it without recursion. I mean, that's not necessarily an interesting thing anyway. I mean, it's just a way to dynamically decide the parameters for this, this if statement. It's dynamically, it basically says you can call this if statement in whatever order. It doesn't have to count from 0 to x. It doesn't have to count from 0 to y. You can count whatever order it needs to count. Is basically all that means. So I don't necessarily need recursion because I could store it in like an array or something of which one I calculated last. Man, I don't know. I don't know if I'm gonna finish this tonight. I am getting tired. Okay, guys, I'm gonna try to work on this later. This is getting me. I'm really tired. I mean, what I could do is put that while loop back in there. And like temporarily set x and y to some value and then like jump back like use go-tos or something. But yeah, this is it's basically recursion at that point. Wow. Okay, guys. Well, I don't know. I could try to do this. Let's store. So this is an example of why it grows, why the Ackermann function grows so big. Because of that. Okay, because it shoots out to the right. The table shoots out. Oh man. Okay, well, I'll pause it for now. And I'll let you guys know the progress. All right, guys, it is the next day. And I've been thinking a little bit about this, and I think what I came up with was, let me think here. So the problem that we have is basically that we want to call recursion. However, what I really need to keep track of is simply whether or not we've already calculated a value. Now I am expanding this table, which is a two-dimensional matrix, which I'm going to assume is okay, although it may not really be okay memory-wise because it may start storing a ton of memory. So this is going to be a sacrifice, okay? We're basically going to be trading memory. Okay, we could use something like a database or hash table or a more efficient method to do this. But what I'm doing is I'm going to make it so that instead of obviously having to recalculate something multiple times, which I could save with this hash value or something like that, I'm just going to store it in a 2D table. Now the problem is it's going to grow really wide, I guess, because n is going to be the width. So the table might have a lot of empty information. It's going to have a lot of zeros, which we won't need. I'll show you in the right here. So it's going to get like really wide as it needs to. In fact, it might get like super, super, super wide. But remember, we're not going to actually necessarily be calculating really like, astronomically large values. I think we're just going to try, doing the more simple, I think it was 4-3 or something, where we get 29. So remember when we do, I think it's 4-3, you get 29. Oh, I don't want that to run again. Do I have this written down somewhere? So, long story short, if I run this 2-3, for example, it's going to count a few iterations, and then we get 9, right? So for what we want here is we want to get we want to call it 2-3 on it, and then just get 9 really quick. And then if that works, then we should be able to find out whether it's 3-4 or 4-3. That gets you 29. So what I want to do is expand the table as needed. And the way we'll keep track, I realized I didn't think of this last night because I was really sleepy. I was getting really tired, and I didn't think of what I could do, but I kind of was thinking of this, I think. But there should be no zeros in the table at all, as far as I know. I had that. Oh, no, it was on my phone. That's where it was, that image. So if the table has no zeros, but when you expand the matrix in a TI calculator, well, guess what? It fills in zeros for you automatically. And because it does that, then all I have to do to see whether I've calculated a value is just check if there's a zero or not. So I can, in a way, do it recursively, but all I have to do is just reduce the variables and then just check that part of the table. So I don't have to really do it recursively. In fact, this is how I should have been doing it from the beginning. I should have just expanded the table to whatever I needed, like this, and then just started at wherever I needed. So I don't even need these for loops, because I don't need to build it out. I don't get why I'm trying to build it out, because I don't need to. I can just update the new m and the new n, and then build it out. But I guess the thing is, if you are trying to find a value at the bottom of the table, then I guess you do kind of need to do this, because if you think about it, I have to save the value which I want to eventually store into that location. So I don't know how I would do that. I guess I'd keep a stack or something, like store it into list 1 or list 2. I could show you guys what I'm thinking. If I had an animation, I could kind of show you what I'm thinking of how I would actually do that. And I think that would be a better way to do that, I guess. Because then I could analyze it for you, and that would be fun, wouldn't it? But it would take a lot of work, and I would need some good graphics and things like that. So, anyway. I wish there were more people, more companies that were willing to work on things that I want to work on, but apparently still 0 people are willing to work on stuff that I want to work on. So, not sure why, because I know it's the future, and I was correct about the future when it came to AI, so I don't know why it's still 0 people who want to help me. I mean, 0 people wanted to help Elon Musk, and now there's hundreds of thousands of people who are thinking he's the boss, but he even tells everyone, no one wanted to do what I was trying to do, so no one tried to help me. That's what he said. So, yeah. Anyway, I guess we could do it that way. The problem, okay, so the problem is that if we do find a 0, it's almost like we need 2 matrices. Well, we don't need 2 matrices, but we need like a stack, basically. We need to be able to store information that we're working on, essentially. So we need to be able to basically take information that we want and store it to keep track of what we want to, propagate back up again if we're not doing it recursively. And that's a problem. It's a big problem. I guess the way we're doing it here, it'll propagate down, but it's only going to propagate down from the top. So as soon as you calculate a value, you won't have to calculate it again. But you may have to come through from the top and see if you came through a value to check to see that it has no calculated dependence. You may have to go through it a few times before you get through it again, I guess. I don't know. So I guess I would need a while loop. It's funny because I initially had a while loop in here. And what's silly is that I actually might need to put one in there because I need to loop. How do I explain this? So maybe I should just show it on a piece of paper for now. So basically what I'm saying is you could think of all the values of the Ackermann function as being on this really big table that just can keep growing, okay? And the way it works is things in this row can depend on things in this row, right? But then they also sort of depend on things kind of both ways. So it kind of goes that way, kind of goes that way. But the thing is, you can pick a spot here, and in a way, in some sense, you don't know how far to the right it's going to depend on n, because n is going to go this way, and m is going to go down, right? So you can pick something over here, but there's no general rule that you can deterministically say without actually computing the Ackermann function already how far this goes to the right. I don't think there's like a way to compute it without already doing the kind of crazy recursion that we're doing just to calculate the function in the first place. So this is going to, calculate on some value here, which is going to calculate on values here and here. And eventually you're going to have these different values that this depends on. And it's not necessarily just going to be strictly, up and to the left of that value. It's not just going to depend on things up and to the left. It's going to go so far out that way, potentially. Now, that's basically what that's what I'm explaining that I'm trying to deal with. If I was doing this recursively, what I'm saying is, first of all, this table, you don't want to, this could go really far to the right, and this table could be really tall. And the problem is you got a lot of wasted area, and it can be really a lot potentially. Because it could just be like, this thing could be a sliver, And on top of that, you also have the problem that you could store zeros here to say, hey, I haven't calculated that. Okay, well, then I'll calculate the next one. I'll calculate the next one. And that's a perfect problem to solve with recursion, because the recursion will save on the stack each one you're calculating. So you'll calculate something, calculate, and then you'll get down to one spot left. And then you'll realize, okay, that's what the value is. And then you go back up and fill them all out so you don't have to go down again. So the way I was thinking I could do it is I could just go like this, where I could say I want this value, which means I want this, this, this. Oh, I fill that in. Okay, now let's restart. I want this value, which means I need this, this. Okay, I know this value. And then, but every time, just to figure out this one value, it would have to propagate down a few times. which still is kind of slow in a way. And I don't know if it's the same growth rate, but it's still kind of slow. So ideally, you'd want to do like a recursion where once you figure out the dependencies, you go back up and you fill that out. And recursion is the easiest way to do that. Although you could have something like a list that keeps track of what the last thing you were trying to calculate was. But that's basically what recursion is doing.
Down here, Mom! It's him. What is it?
I'm recording.
Oh.
That was my nephew. So basically, I could compute this function right here, and then this one in order to compute this one. But in the process of doing this one, to say that I'm complete doing it, then I have to say that I was computing this one. So this one helps define where I was looking for this one. So on the stack, I basically have to push onto a list. I have to tell it where I was last. So I was looking for I was looking for the one with m and n-1 last. But when I was doing that, before that, I was looking for m-1 with that value. So I basically would have to store all that information on the stack, which is what recursion does. So I might get rid of that altogether, but I remember I said I wouldn't do recursion. So basically, the new thing that I have to try to figure out how to do is essentially I have to store things on the list. So we'll probably use like list 1 or something, and it will say, you know, what I was trying to compute last. So it'll have like, you know, it'll have, maybe we'll put zeros or negative ones. So when we have a -1 and then an m and then -1 and then an n, that might work. But if we've been trying to figure this one out, then we don't know what one we were trying to fill. So for that, we might have, you know, we might have our -1 and an m, and then just a -2 or something, to say -2 means that we're looking for that kind of n. Right? Maybe. Yeah, I'm not sure. Man, that's gonna be tricky. Okay. Okay, so how do we do this? We didn't use list 1 yet. Okay, so list 1, we're going to push 1 onto it. No, we're not going to push 1 onto it. We're going to come down here. We're going to look at we're gonna get rid of the for loops. Okay. And what we're gonna do is we're actually just gonna have a while loop. Yep. Okay, so we store 1 into A11, which is fine. We're going to delete these. And then I'm just going to have a while loop. So I'm going to say while let's see, length 1. I think we have a length function that we can use on this list. Okay, so I can say basically while the dimensions of list 1 is greater than 0, right? Okay, so if I store 1, 2 into list 1, then I delete, I don't know if I can do this. Delete var, list 1, 1, list 1. Oh man, this is nuts. I do not like that at all. Okay, I don't know if there's a way to make a list smaller. Is there? Is there even a way to make a list smaller? I guess it doesn't matter. So, yeah, because I'll have a counter. So, I'll have a counter, right? While c is greater than 1, we do all this stuff. And c is going to be... however deep we are going in our kind of pseudo recursion, I suppose. So I'm going to store 1. Okay. Okay, so we have -1, m and n stored as into list 1. What that's going to do is it's going to allow us to know that this was our first thing that we were looking for. We were looking for m comma n, right? when we don't find it, we're going to look for our next one. Okay. So then what we need to do is we need to take... So this one, we don't need to worry about it. We can just store our thing into there. This one... Okay. We need to do another if inside of here. So we do if matrix A of m comma 2 equals 0, then we do something. Else end. That's if it's greater than 0. So in this else right here, we're going to see about calculating the M2, right? So now we know that our C is 2. So what we do is we add to it then. Okay, so we add to our C. We say C plus 1. Let's see, list 1. Let's see, C times 3. There we go. -1, we're going to put into list 1. C times 3 minus C times 3 plus 1. Okay. So if C is 1, actually, hold on a second. If C is 1, then we will have 1, 2, and 3. If C is 2, 2 times 3 is 6. Six, 7, 8. C is 3. We'll have 9. Three, 4, 5. I think C should actually start off at 1, because we have 1 there. So C, C, this is the 0, 1. So 1 times, so if C is 1, that's pointing at our next 3. Okay, so basically this is our stack. 1 times 3 plus 0. Okay. All right. Okay. So we're calculating this before we can store it here. Right? So what we really want to save is this. This is what we want to save. The M and the N. Although I already have it here. So that's a problem. Let's see, 1, 2, 3. Sorry guys, that was my alarm. Okay. I'm gonna pause this because this is torture. So I don't want to put you guys through torture. And that'll be that for now. Thanks. See ya. Okay guys, so it's been a couple of hours since that alarm. If you remember when my alarm went off, it's been like almost 2.5 hours since then. Oh, there's my handy dandy 29. As you can see, I'm getting, I have something running here. Sorry that I didn't show you all the interesting stuff going on. So I'm going to go through the code and show you kind of what's going on. So I'm going to do, let me just run a simpler one really quick. I'm just going to pass it 2, 2. You'll see it kind of shows me in the iterations as it's filling out the table. So this is the table where n is across and m is the height. And it resizes the table as needed, and then it finally gets me the 2, 2 value would be right here. And it didn't show you the table, but if you update it one more time, it's going to be right there. So so we have call ack, which calls Ackermann, which was part 1. Then we have ackmem, which memoizes, and it doesn't use recursion. So I'm using list 1 and list 2. And I'm using a couple variables here. And you notice I started deleting some of these variables just because I was trying to debug and I was confused as was what was going on. And I'm going to explain to you guys why I had to debug for so long and what was actually going on. So I'll just explain my code and what it does here. So this is all initialization code right here. You just pick whatever m and n you want, and you can already just begin the size of your matrix as that, even though you will be making it essentially at least wider. Yeah, I don't think I even need this necessarily, but I'm just initializing the first, the first value. But I don't think I even need to do that. C is the depth, basically, of my quote-unquote recursion, which I'm manually, essentially emulating. I'm going to show you a couple things I had to fix that I had to catch, which was what I was doing. So you start off with one thing on this stack that I have, which is list 1. So I'm treating list 1 as a stack, and C is like the counter for the stack. So that's how I'm manually doing the recursion. I'm just using the -1 as kind of a character spacer, and then M and N are the things that follow that. So here I just check to see if wherever I'm at, if it's -1. If it's not, then it will print error. It never printed error because I always had it, matched up correctly. So that was just to make sure that I was reading the list properly. And I didn't want, overlapping numbers and all that stuff going on. So that's why I, just used a -1 to space everything out. Now here I subtract 1 from C. So every loop, I'm subtracting 1 from C. I'm assuming that I'm basically going backward 1 on the stack to try to pop something off the stack. That's the attempt. So basically every iteration, while C is greater than 0, I basically subtract 1 from it. So obviously at the start it turns 0 here, but obviously it doesn't know the answer right away, so it has to actually add something on the stack. So I'll show you that in a second. So here we simply just multiplying by 3 because there's 3 numbers, -1, and then we have M and N. and then I just add 1, 2, and 3 because obviously TI calculators don't start at zeros, they start at ones with the matrices in the lists. So we just have to add 1 for each of those things. If n equals -2, now this is checking to see if I did the -2 spacer. So you'll see here, this is one of my debugging systems, but if you start off with A22, you want to find out what that is. Then you use the equation up here, right? And it's our else case, so we have 2 Ackermann functions, one inside of the other. So the -2 represents the box that we're going to calculate later, and then we have to figure out that Ackermann function recursively. So this is basically a sanity check to see if it's recursive. Now this is the thing that took me forever to debug. I used to just have r stores n, and then what was happening was the matrix just kept getting wider and wider and wider and wider and wider, and just kept getting, just forever it kept getting wide. So I would just ask it, what's 2, 2? And then it would go all the way down to like 50. It was getting really wide, and I was so confused. I couldn't figure out why it was getting wide, and now I know why. I did this by hand, and I realized once I calculate all the way down till I get 2 here, and then I start propagating back up, now not only am I getting return values, but I'm getting values to put into the box, which I do fine, right? I even say, oh, I get a 3 here. But then what happens is I don't automatically assume that this is the return value for this. I just assumed that this was what gets replaced in the -2. Now the problem is that I store this in the variable r, so it's in the variable r, and even when I'm looking at this expression right here, I set the n to 3. So I'm looking at it and I'm like, oh, how do I figure out 1, 3? And then I go down here and I calculate it all out. But then I realize, wait a minute, this is eventually going to return a value to here, right? And it's going to return something to here, and then this is still going to think it's a box. So if this returns like 10 billion, it's going to return 10 billion here, and instead of this calculating 1, 3 or thinking that it's done, it's going to say, oh, I want a 1, 10 billion, because I never set it. I only set this temporary variable. I never set it back to the actual list itself and rewrite it into the list. For some reason, I just never thought to do that. And I kept thinking, how is it? Is it returning the wrong value? What's the last, And it was returning the correct value first, and then it went off to calculate its actual value. So I was kind of doing that in a silly way, because it's kind of what I was doing. It's like I was returning a value, but in another sense I was returning a value to insert in a list. And this is all manual. This is stuff that I'm doing that should be built into a programming language already that I'm doing manually, essentially. So anyway, now this is where we break apart our 3 cases. So if m is 0, then we do this stuff. Now you'll notice that I have this x and y in a resize. So I actually wrote another program called resize because I had to call it in like 3 different spots, and it was going to make my code really confusing if I didn't put it like in a separate spot, because it's like 5 lines, right? And then these lines would have m's and n's and stuff like that, and I'd have to rewrite them, and it would just get insanely confusing for me to search through my other code. So I decided that I was just going to make a function essentially called resize, where I just set x and y, and then essentially I use list2, which is a list that I'm not using already, to save the dimensions of matrix A, because it doesn't let you like do dimensions of A and then kind of put parentheses after it. You can only put parentheses after something that's list, because TI Basic doesn't support that syntax. I don't know why, they just don't. So then down here we have x, y, and then we store that into the new dimensions of matrix A. So basically these are just max functions. We see if x is bigger or not, we see if y is bigger or not, and then we just put the maximum of the new size there. So we're never shrinking it, we're only making it bigger. We don't want to shrink it, because we don't want to like erase numbers we've already calculated. That just doesn't make any sense. And if we already needed the space, then, we've already taken up that much space anyway. And plus, if we're making it bigger, we're more likely, because of how the Ackermann function works, we're more likely going to reuse those values anyway. So just because we made the matrix taller doesn't mean we want to cut off all the ends on the side. We just want to leave them. because those are definitely the ones that consume time. We only want to calculate them once. So here we resize it basically before we check it, because if we check it and it's the wrong size, like if we check it and the m and n plus 1s are not in the matrix size, and it crashes. So we resize it here before we do this, before we even store the value. I'm not even just checking the matrix, I'm just storing the value, but I'm even resizing it for that, just to make sure that the matrix can handle just adding that number in there. Okay, so here obviously is the first case, so we got that handled. If m is 0, then we just store it to n plus 1. That's going to be our value. Okay, otherwise if n is 0, then what we do is we store m in 2, and the reason why it's m in 2 is because it's actually m minus 1 in 1, but remember we add 1 because we're just dealing with the matrix here, so we're resizing the matrix, so that's why we add 1 to each, and that comes out to m in 2. Same here, we're checking to see if it's greater than 0. Now this is where we branch. For the second case, we're going to branch, and we're going to have 2 cases for that. So either we're going to be returning or we're going deeper. So here we check to see if there's already a value calculated. If there is, and we're just going to be returning. We're just going to look at the value, and we're going to say, okay, that's going to be our value, and then we return it. We've already subtracted 1 from C, so when we're done, we've already subtracted 1 from C. We're going to go to we're going to pop the next thing off the queue and or the stack and just keep going back. But if we haven't calculated this value yet, then we have to do that now. So we've already subtracted 1 from C, but now we not only have to add something onto the queue, but we have to make sure we're not telling it to overwrite what we're looking at now, because we need to come back to it. We need to come back to this m and n. So that's why I add to C twice here. Once up here to change, so that I can work with it right here to add something new to the stack, and then I have to add to C again to point at whatever comes after this, because this is then going to have to be calculated. So not only am I not removing my current thing off the queue or off the stack, I'm also adding this new thing to the stack. So I'm going deeper instead of going back. So basically it's one or the other. So one of these essentially just makes up for the fact that I subtracted 1 from C, and then one of them basically makes up for the fact that I'm even going deeper too, by 1. And of course, I add 1 to C so I can edit it here for the next thing. Of course, I add a -1 for the first of the 3 elements, just as my parser thing. And then, since we're in the second case, we have n minus 1 and 1. So that's our second case, m minus 1 and 1. And these are just values that we're storing into the list, so we don't have to add 1 to them, because it's not the matrix. That's only for when we're dealing with accessing coordinates in the matrix, which we're not doing here. We're just storing the raw values. Okay, and of course there's the third case, which is if they're both greater than 0, or if they're both of them are not 0. So of course we have m plus 1. So if you look right here, we have all this stuff right here. M plus 1 stores x and n stores y. That's for resizing, and I'll explain why it's m plus 1 and n. That's because we're checking, the first thing we're checking is this. Okay, remember we're adding 1 to each. Okay, now I'm using D because there's a couple of cases that I'm branching from and combining here. So I'm just using the variable D to store a 1 or 0 to check. So if that's true, okay, if that is greater than 0, okay, because I've already resized to make sure I could check this. Now if that's greater than 0, that means I already calculated that value. But that doesn't mean, just because I have this value doesn't mean I have this outer value. So it also checks to see, do you also have this the outer value? So I say, okay, well, first set D to 0, and then we're going to resize again, but we're going to resize based off this inner thing being the coordinate, right? So now this could get really wide, so we don't know what this number is. It could get big. and we're going to make sure that our y is that big. So then we resize it for that, and then we check to see if that entire expression is set. So if we just resized, it'll be 0. But if we already set it, it's going to be more than 0. So now if both of these values are set, we get a 1. Now, otherwise, it's not going to set that 1 to D, and that one's going to be 0. Or this one has already failed, and we reach the else, which is going to be a 0. So then we come up here and we check, is D 0? If it's 0, that means it's not both of them are set. If it's 1, then that means both of them are set. So if it's 0, what do? We need to go deeper. So we add 1 to C. Now we add 2 things on the stack. So 2 different expressions, both of them starting with a -1, right? The first one's the outer one, which is the m-1. And then we put a -2 for that to say that the second one's not calculated yet. And then we push the second one, which is an m and an n-1, onto the second one. And then we add 2 to C again. So see how we're adding 3 to C total. One of them basically says, don't get rid of what's already on the stack. And then 2 of them say, okay, we're actually adding 2 more things on the stack on top of that. Okay, now if both of those values had existed, that means we don't need to go deeper, and that's what this else is. So I just calculate the inner value here, and I store it into B temporarily, and then I just insert B in here, and of course I have to add 1 because it's coordinates, right? This B is going to be the raw value, so I'm going to have to add 1 to it. So all I'm doing here is I'm calculating this inner one right here and adding 1 to them because it's coordinates. And then I'm calculating the outer one, which this one's going to be B, and then this one's going to be M because we're adding 1 to it because it's coordinates. And then we're storing that into our MN, which we're adding 1 because it's coordinates. You get what I'm saying? Now we're going to end all these different cases for the loop. Of course, there's the outer loop, right? And then what I do here is I resize to make sure that we actually have somewhere that we can actually access our return value. Because I had a problem initially with just this existing in the first place. Because what the reason is because if we're going deeper, this value might not exist. But if we resize, at least it'll just be 0, and we can just set R to 0 just so it's something, just so that this doesn't crash. Okay, but the point of this code right here is for when we're not going deeper, but when we're popping back on the stack, we just set this value, but we want to save it in a temporary variable R so that we have a return value saved for when we're setting the -2. So usually we won't need this R except when we're setting a -2 value, because usually we'll just have this value saved and then it'll recalculate the expression using this the next time around. But it's not, but sometimes we'll need obviously to replace that -2 as soon as we can, because the first round we replace it. So, and then of course at the very end we just display the answer. So after we're done with the loop of the entire Ackermann function, we go ahead and we just display what our final answer is, which is going to be back to what our original m and n were at the beginning. So there you go. This Ackermann function, what's nice about it, it's much faster. What I'm going to do is instead of this is what I'm going to do. Hold on. Here, what I'm going to do, well, I'm going to go down here and I'm just going to say 0 store as, and I'll just say T. Okay. And then I'm not going to display A, but I'm going to add 1 to T. So T plus 1 stores T, right? And then I'm going to display T. Okay. So now when we run Ackermann, okay, when we run the old call ack, right? And when we run, like, let's say 3-3, remember it goes like really deep. It takes forever. Oh no, it's 2 3s takes forever even. You know what? No, forget that. We're gonna do 2-2. Okay, so remember this one I think went up to like 2. Oh, that's just 27. Okay, Well, let's try Ackermann. 2, 2. So this one's going to be obviously a little slower because it's got more overhead. But, okay, I guess it still needs to go to 27. Because you're only doing 2, which means it still needs to calculate those initial values. Okay, well, let's try... I don't know if I want to do 2, 3. Let's do 2, 3. Let's do 2, 3. Okay, so that going to 44. Okay, and then call Ackermann. So this one's going to be slower for the smaller values, but once you get to like astronomical values, like let's just say 5, 5 or something. Okay, hold on. That went to 35 instead of 44, right? So this seems like this one's faster at first, right? But I swear, once you put in like 10, 10, this one is gonna be able to finish. No, this one's gonna take till the sun burns out. The other one's gonna like be able to finish. Oops, 5, 5 is way too big. 3, 3. So this is call Ack, and watch. This is gonna, it's so big of numbers, right? It's probably gonna go to like 200 or something. So there we go. It's still going. Man, what was the number that was it 3, 2? I don't know if I should have done 3, 3. I think that one's too big. I think I should have done 3, 2. Uh-oh. How big is 3, 3? Hold on, let me check, guys. I think 3, 3 is a little big. I know 3, 2 is only like 26. I don't know what 3, 3 is. It might be really, 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 really big. But I'm not sure. See, that's the crazy thing about this function is it explodes insanely. It's not like tree 3. If you ever watch number file, tree 3, I guess, is like super, super explosion. But the Ackermann function is known for being like a super, super high growth function. It's just insane. It just explodes. It's just boom. It's just like numbers that you can't even describe with exponents or anything. It's just the recursion like multiplies itself like recursively. That's how it works. It's just insane. So what I'm going to do is I'm going to do 2, 3 because I know that this one stops around like 200 or something. What? Oh, I'm sorry. 3, 2. There we go. Okay. So this one is going to give us 26, but it's going to take... Maybe I should have done 2, 3. Is 2, 3 really just 9? I guess. 2, 3, 7, 9. Yeah. Oh, 3, 1 would have been a good one. I think 3, 1 is a good one. This one is 26. So this one's fast, right? But it has to recalculate everything. So that starts multiplying on itself almost like exponentially. This function takes like a few iterations. You know, you have to go past like 3, 3 at least. It takes a little bit. And then it just explodes. And the number of like times it starts calling functions that it already called just explodes. It just calls the same thing thousands of times. So here we go. Here we go. 541. 541. and then it got the correct number, which is 29. Okay, now check this one out. What was the other one? 520, 521 or something? It's, over 500. This one's not even going to be close. This one's only going to be about, I don't even think it's going to be, I'd say you could probably get, I wouldn't even say n squared over 2 would be a good guess necessarily. But I don't think this one's going to get close to the 500s, I don't think. But notice it's significantly slower. Oh, there we go, 133. So you notice it starts cutting down more. And that the amount that it cuts down is going to go, I think it just goes all the way to like 99.9%. Like it's just going to go ridiculously. Because most of those, you can see how most of those calls already, when you just pick a very small number, we just picked 332, right? That's like such a small number. And look how much it's already cut down. So there you go, guys. That was Ackermann function. Versions 1 and 2. So we have call ack, which calls Ackermann, and it's recursive. And then we have ackmem, which is not recursive, and it also memoizes the function, which are two criterion that we wanted to fulfill. We wanted to make it non-recursive, and we wanted it to remember things. And then we also had resize, which Ackermann uses. Ackermann uses resize because resize just contains some more just annoying code that I use like in 3 different spots, and I just didn't. We can't do lambdas and things like that, so there you go. That is coding with Tim. Another episode 30 something. Thanks to my one Patreon supporter once again for supporting me and helping me do this. I will see you guys later. And please give me suggestions for any more episodes that you want to see. Bye, guys.